Welcome. So, we were discussing about speed control of induction motor as it is done in modern days. Now, I will also discuss about some in this class another method which I just pointed out, but because of academic exercise it will make you understand induction motor in its better way. I mean, it will strengthen your understanding how that control was done. But before that, one point I want to tell. See, the moment somebody is making a connection like this, that is he is now no longer fed by a constant frequency supply. That was the problem in earlier days. People used to say, okay, induction motor, it cannot really replace a DC motor where speed control is so easy. Here only at discrete level you can control some speed, that too with complicated things by changing number of poles, because frequency of the supply was fixed 50 hertz. But nowadays those things have gone and you can control the speed nicely. That is, the numerator is a better option, vary frequency, and that can be done easily by modern day inverters. Another interesting thing is, in this type of this thing, it has to do with some starting. See, in the starting also we adopted so many things. Direct online starting, okay, direct online starting. On small motors you can do, as I told you. But then you can have reactor starting, you have to purchase reactor, this, that, then auto transformer starting, or then star delta starting, some switching is to be done from delta to star and so on, or start to delta. At the time of starting star, switch over to delta after machine has picked up speed. But here if you have an inverter, you can also think of starting the machine in this way. Do not apply full voltage, supply it from an inverter like this and increase the voltage and frequency slowly with this control, such that V by F ratio is constant, so that machine is never saturated, and go up to the rated voltage and frequency. There is no question of any large inrush current coming in. So, this point I am telling because of this, that nowadays induction motor starting problem can also be reduced with the same inverter, with some proper I mean this control of voltage and frequency will be some, you will be writing some codes here and there and get the get pulses of the inverter switches, so as to make V by F constant during starting process and so on. So, the way you look at induction motor should be also based on this understanding, that is very important. Okay. So, that was the thing. Okay. One just method, as I was telling. So, this is the speed control of induction motor, and it can be also done. That is why nowadays you will at least read the newspapers and the development of traction in India. People use induction motor drive, not DC series motor, with this inverter and then converter, all the controls will be there, and you can use it in traction as well. They are slowly replacing this old DC series motor. DC motor, the problem is major. What is the problem? Commutator segmented brush, you have to replace this, that. Okay. But in case of induction motor, and particularly cage induction motor, no matter whether it is cage, wound, everything, for every motors you can vary the frequencies to vary the speed of the machine. nonetheless, as I told you, just this an interesting, earlier days also people thought, because at that in those days there were no variable frequency supply was available, no inverter, fast acting inverter was there. So, this method is, listen it and see how the concepts of induction motor was used. So, it is like speed control by using two 3-phase induction motor. Of which one must be wound rotor, one must be slip ring type, one must be slip ring type, and slip ring motors are costly because slip ring are there, brushes are there, and other maybe slip ring or cage, because the cost is reduced. What is done is this, this is the one motor, this is another motor. Okay. Its rotor. Now, this is the stator and rotor of the first motor, and these are the terminals. I am not drawing this slip ring and brush arrangement. And you have another induction motor, say like this, and this is suppose a cage induction motor. Now, what is done? And these two motors, rotors are mechanically coupled. So, these two motors, I am not showing it here, another line I have to draw. These rotors of these motors are mechanically coupled. Which means that rotor can only rotate, the rotor speed of both the motors are same, it has to be if they are mechanically coupled. Now, what is done is this, idea is very interesting, and as I am telling you, you give the first machine, machine 1, and this is machine 2. First machine you supply with rated voltage, rated frequency. And suppose the number of poles of this machine is P 1 and number of poles of this machine, they must be different number of poles P 2. Now, what is done? The rotor of the first machine will supply the stator of the second machine. That is how it is connected. Okay. Now, suppose let us assume the supply phase sequence is such that the stator field of or resultant field of the first machine moves in the clockwise direction NS1, and this must be equal to 2f by P1, because its stator is supplied with frequency f, and suppose the rotor speed is also in this direction NR, because speed of this rotor is dictated by NS1. I draw it like this, and the sleep of this machine is this one. Okay. Now, look at the second machine. Second machine is supplied with some balanced three phase voltage, definitely, because these are all balanced machine, but frequency of the supply of the second machine is how much? What is the frequency of the rotor currents? S times the supply frequency here. So, S1 f is the frequency here of these currents. Then the second machine, I will say, it is supplied with a frequency S1F. Therefore, this second machine stator winding will also carry a balanced 3-phase current, but of frequency S1 into F, and thereby it will produce a rotating field Fs2, and suppose the way it is supplied, the phase sequence supplied to the second machine is such that it also rotate in this direction with a synchronous speed ns2. And what will be the value of this synchronous speed? It will be 2f, but f is s1f by p2. This will be the speed. Okay. Now, the rotor speed, of course, because they are coupled, they are same, they cannot change. So, this will be the situation, that is, from the rotor of the first machine, you supply the stator of the second machine, both these machines are coupled, mechanically coupled. So, speed is nr like this. Now, we write down what is the value of nr from this machine. Nr will be equal to 1 minus S1 into ns1, and this is equal to 1 minus S1 into 2 f by p1. And also from this machine nr, same rotor speed, will be equal to 1 minus S2, suppose the second machine is running with a slip S2, into ns2, and this will be equal to 1 minus S2 into ns2. ns2 is this, that is 2 S1 f by P2, and because these two are coupled, therefore, these two must be equal. So, that is 1 minus S1 into 2 f by P1 must be equal to 1 minus S2 into 2 S1 f by P2, where P1, P2 are the number of poles of the machine. Now, you can see this 2f goes from both the sides, and you are left with 1 minus S1 by P1 here, and here what you will be getting is S1 minus S1 S2 by P2 here. Now, the next step of simplification is centered around the fact that both S1 S2 slips are small, therefore, neglecting S1 S2, the product of two slips, because slips are small compared to S1, S1 S2 will be small. If you neglect, then approximately I can write, you can get a fair idea of the synchronous speed as equal to, is that clear, S1 minus S1 by P2 here, or if you take this 1 by P1 here, and this side if you bring it, it will be S1 by 1 by P1 plus 1 by P2. Therefore, S1 will be equal to P1 P2, P1 P2, P1 was there already by P1 plus P2. P1 goes, and slip at which the machine will run approximately is P2 by P1 plus P2. And once you get this, then you say that this nr rotor speed will be 1 minus p 2 from this one, 1 minus p 2 by p 1 plus p 2 into 2 f by p 1, which is equal to, if you put it here, it will be twice f by p 1 plus p 2. Is that clear? So, very interesting idea, that is, the rotor speed will be very close to 2 f by p 1 plus p 2. Now, I will not go further into it, but I will tell, because see this problem also strengthen our understanding of 3-phase induction motor, that okay, it is supplied, phase sequence is important, direction of rotation, then by simple algebra and knowing the facts we have learned earlier, that is rotor speed is 1 minus s n s 1, synchronous speed is 2 f by p 1, etc. We find that the speed of the induction motor is 2 f by p 1 plus p 2. It can be shown, I will just write down only these facts. If you supply the second machine with two terminals, here I have assumed they are supplied in such a way the stator field is rotating in the same directions, but you have another option. You supply the second machine stator with phase sequence reversed compared to this machine, such that what I am telling, if f s 1 is moving in this direction, f s 2 is moving in that direction, you do it, then you can show that the rotor speed, once again with this same type of argument, this I leave it to you to mathematically show the other speed when the phase sequence applied to the second stator is changed, then such that f s 1 and f s 2 move in opposite direction, then it can be shown n r is close to 2 f by p 1 minus p 2. It can be similarly shown. Therefore, it looks like I can get 4 discrete level of speeds. One is you only run this machine alone, second machine it is coupled, let it be there, then you can get a speed of 2 f by p 1. Use the second machine only, first machine do not connect anything, then you will get a synchronous speed of 2 f by p 2, and connect these two in cascade so called, okay, that is the stator of the second machine supplied from the first machine rotor, then you can get another 2 speed p 1 plus minus p 2. So, 4 sets, but nonetheless these speeds are discrete. As I told you, to control the speed of your load, you now require 2 induction motors, then a costly motor, slip ring of similar ratings, and it will supply the load. So, nowadays no point in applying this in practice, it looks like, although these were once upon a time they were used very much. See, this is how people fought with the how to control the speed of an induction motor and make it a very good drive, making it a real competitor of DC motors. That is, with the advent of rectifier and inverter set, those can be very nicely done. Okay. So, this is the what is called, I just told, at least gave you idea how to start an induction motor. That also has changed, as I told you, but those are traditional method, go through it, nothing wrong in it. And then speed control I talked, And then what is the third thing which is important for any rotating machine? I told you electrical braking. Any motor, one must ask how to start it, how to control the speed, and how to electrically brake it. So, braking. Of three-phase induction motor. What is this? You know, braking is very simple to understand if you go by this. When we ride a bicycle, I want to stop quickly. What do I do? I apply a mechanical brake, that is some brake shoes will touch the wheel and your cycle will come to a stop. Or what you can do, you are riding a bicycle, you want to come to a stop, you simply stop pedaling it further. Then it will also come to stop after, of course, traveling some distance, not quickly you can put it back. Therefore, the essence of braking is this one. If something is rotating, you want to bring it to a stop, one way of doing it, you simply disconnect whoever is driving that rotating body. Okay? Simply, for example, if it is a motor, disconnect it from supply, stand there, it will come to a stop eventually, because no flux, no current in the motor, it will eventually come. So, that way it will come. Now, what is the essence of the thing? Essence of the thing is how a rotating system, when it comes to stops, what has happened? Whatever was its kinetic energy, that must have dissipated somewhere, that is why that fellow has come to a stop. Therefore, to bring a rotating mass into a stop, you must see that how the kinetic energy stored in the machine is evacuated from the system. When we apply brake, what you are doing, that kinetic energy is dissipated as heat in the brake shoes and of course, in the road and tire friction. All the kinetic energy will be dissipated there, your brake shoe will become hot. Put your brake hard, it will come also stop very quickly, but all the energy will be dissipated fast. In the brake shoes, it will become much hotter. Therefore, the essence of the thing is that if you have a rotating thing, and the question of braking means that disconnecting, I want to bring that motor come to a stop very quickly, but I want to do it also fast. So, okay, you can use a mechanical brake, is not, to do it. But mechanical brake, once again maintenance problem will be there, it may not be, I mean you cannot control the braking torque, all these things will come. Electrical braking, by braking of motor we understand that how electrically it can be braked. So, to brake the induction motor, there are three popular methods. One is called braking, is called by plugging methods, plugging. Then another is DC dynamic braking, DC dynamic braking. And another is called regenerative braking. Okay. These are traditional methods. Nowadays, okay, all the breakings can be done also with that inverter units. Okay. Acha, before I discuss this, see, so far I have drawn the torque slip characteristics as a motor mode and told you that slip can be between 0 to 1. You recall this is the thing. Whichever way you draw, I think you are now habituated, either you draw this way or that way, what to put s equal to 0. So, this is slip and this is 0 slip, synchronous speed, and this is this. This is the torque slip characteristics, and I told you this is the motor mode. Fine. And I say motor is operating, a machine is operating as a motor if slip is positive, like that. Acha, you now imagine this circuit. An induction motor is there, and I have drawn a slip ring machine. Okay. Motor mode, it is running fine. A, this is supplied to be A, this is machine B, and this is machine C. Okay. And these are suppose supply terminals, supply AS, supply BS, and supply CS. What I do here is this supply A, I take once again a triple pole double throw switch. I am sorry, this is the thing, triple pole double throw switch, and bring it here. This is A, machine terminals, I bring it here. This is C and this is B. And I connect it like this, throw it this side. The other side I will discuss, but the point is, if you connect it like this, the machine is supplied with a phase sequence ABC, rotating field will be moving like this, and rotor will rotate at some speed nr, and suppose it is running steadily, and this slip is ns minus nr by ns. Now, what I will do is this, this machine I will at some time I feel I will change the supply phase sequence to the machine. That is, supply AS will be AS, but BS and CS I will interchange here. BS I will connect to C and CS I will connect to machine B. Then what do you think is going to happen? Motor was running fine, slip AS, but suddenly I change the supply phase sequence of this motor. If you do that, then I know the rotating field produced by the stator will move in the opposite direction compared to the situation when it was supplied with supply phase sequence AS, BS, CS. But rotor speed cannot change instantaneously. Therefore, when you execute this switching at t equal to say 0, then at t equal to 0 plus, what you have done is the rotating field produced by the stator is moving in the opposite direction frequency has not changed, with same synchronous speed it will rotate, and at t equal to 0 plus rotor speed can also change instantaneously because it has got inertia. Therefore, this leap at which the machine is running we will calculate and show it that it is equal to 2 minus s. We will continue with this. Thank you.